All right. Should be able to zoom in once on this, can I? Yeah, perfect. All right, so let's, why does it always reset back to the top? Okay, so we talked about shells last time. So everything was about how do we interact with our computers, and they're not always the same. Minimalistic data types like icons, files, these are all things that whenever we solve problems within our operating systems, we have to solve them in terms of the tools we have available. So any file system type problem, we're solving in terms of this file data structure, that kind of stuff. So understand that it may or may not be a limiting factor, but it's just another example of having to solve problems in terms of the tools that we have available to us. We just don't have this this latitude to just be able to reinvent everything and say, here's a brand new operating system. Obviously, creating a new file system that wasn't based on our generic file data structure is going to be problematic. Nobody's hard drives are going to work, and all these things that your operating system sort of kind of relies on no longer going to be supporting what you're trying to accomplish. Let's see. Okay, there's our shell stuff. Kind of talked about it relative to our GUIs. Very much so from a computer scientist skill set perspective. I would say that even today, command line is more powerful than the GUI. With our GUIs, we have to rely on somebody building kind of a tool that brings in a whole bunch of different skills for us to be able to do. Where last time I think I showed out in the terminal, we're able to utilize all these programs that already exist. And what's kind of built into the concept of the command line shells is this idea of being able to redirect the output of one program into the input of another program and that kind of stuff. It's part of the standard for a command line shell, where that's not the case. That's not part of how we use our graphical user interfaces. So I guess for us, one thing to keep in mind, especially the IT people, I think we use the example of if you're remoting into a switch or a router that's under the floorboards halfway across campus or something like that, you're likely not going to be using a graphical user interface. We started talking about system calls. And again, whenever we're writing user level software, whenever we're writing programs ourselves that are running on an operating system, those programs have to be written in terms of the tools that are provided to us by the operating system, those system calls, whenever we need to interact with the operating system. Some system calls let us get away with a lot. Some system calls don't. We talked about Java, how Java's one additional layer, how we have our Java program talking to the Java virtual machine, who then makes specific system calls for us and may or may not be able to make certain ones because it's not running as the administrator, that kind of stuff. Let's see. So, types of system calls, these fall into the exact same categories as we've talked about at the high level for our operating systems. So, things dealing with processes, things dealing with files for the file manager, for the process manager, that kind of stuff. Device management, let's see, whatever. All that jazz. Then we have some comparison between Windows system calls and Unix system calls. So Windows, create a process is called create process. Unix, we fork. Exit process exit, wait for single object, wait, so on and so forth. All right. We can see here that the Windows approach is very much influenced by object-oriented naming conventions. You know, where the names are very descriptive. They really follow when we create a class in Java or something like that, how we would name that class. Whereas Unix are IOCTL, set console mode. That seems to be not that intuitive, right? Okay, so now some examples as we talk about kind of the evolution of our operating systems, and we already kind of made a pass at this at the high level, but from an MS-DOS perspective, we have single tasking. That shell, the DOS prompt, is what pops up right off the bat. You know, we don't get a graphical user interface with it. So simple method to run a program, so no process is created. Why is that? Why wouldn't a process be created in DOS in order to run a program? Go ahead.
You don't need to create a process to run it. You can just run it, can't you?
Okay, so you just reworded my question. So, so why not? Why wouldn't you have to create a? I mean, obviously the answer must be yes.
Direct access to memory and to.
What's the purpose of having a process? When we think about process management on our computer, and we think about process as a program running on the computer. Well, actually, it's called a job when it's actually running. It's a process when it's ready to run, whatever. What's the purpose of that process data structure? Why do we need it? For multitasking. Yeah, so the idea of a process, I mean, last time we were kind of focusing on this idea of trying to make these connections to our programming life where these things are data structures, just an object for keeping track of crap that we're interested in keeping track of related to a process, right? And at the end of the day, the reason why we need a process data structure is your process might only be running for a small period of time. So we need to keep track of where we left off, where we need to pick up from when we start back up, things like that for multitasking. Well, if we have a single tasking type operating system, the concept of using a process data structure no longer makes sense. Why do I need to keep track of this extra crap when my program's going to start running and it's going to be done running when the user closes it? It's never going to leave the CPU, or it's at the very least never going to leave the CPU on its own accord. It's possible behind the scenes, the operating system kind of pauses your process for a little bit, maybe has some hard-coded things where it kind of stores the state temporarily while it goes and does a couple of things on the operating system. But in terms of user-level processes going from one process to another process doesn't exist in DOS. So why use a extra complication? Make sense? Same thing, single memory space. We haven't talked about the specifics of memory too much, but why do you suppose there's only a single memory space in DOS? Don't need to subdivide it for storage of different programs, right? Looking ahead, we can imagine that, in a multi-tasking type operating system, we're going to have multiple programs launched at one time, and we therefore need to, at the very least, consider memory in a more complex way. Since we've already mentioned that we need to load parts of our programs into memory, enough of it to run, but not so much that we run out of memory and all that jazz. Speaking of which, Levi, how much memory do you have in your Mac? 4 gigs should be plenty.
It's like I've got like Chrome and other stuff running at the same time.
It still should be plenty. Is it just like a really old Mac?
It's pretty
Oh.
It runs, it just takes like a minute or two.
Only the first time you launched once the simulator's up, it's good?
Yeah, once it's running, it runs. The simulator runs fine.
I got that. Initial simulator launch takes forever.
Yeah, it takes a long time.
Got it. Let's see. So just like this. So when we take a program, we load it into memory, overriding everything except the kernel. Okay, so we basically have in DOS, there's a kernel space that we reserve. And that's where the operating system lives. So that's no touch. We can't write to that space. The whole rest of memory is 100% for the access, the use of the one program that's running. Okay, so when we launch a program, it's overwriting whatever other program used to be in memory and doesn't have to erase what was there, just moves right on it. No harm, no foul. Now, what's interesting about that is I want you to kind of consider for a second what it would take as a programmer to implement DOS. Now, while we can probably assume it's not a simple program, right? Imagine how much less we have to worry about in a simpler, more primitive operating system like that than our modern operating systems. We don't have to run more than one program at once, so that's a whole pile of stuff we don't have to worry about. We don't have to have more than one thing loaded in memory at once, another pile, so we just keep throwing things out the window, and now like, oh, well, chances of DOS having huge bugs in it are fairly small, right? Not as many moving parts, stuff like that. When a program exits, the shell is reloaded. So the shell is our default user program. It's where it's kind of like when we say all programs begin and end with main, all user applications begin and end their launch with the shell. We launch it from the shell, and when they die, the shell is automatically reloaded for us to then again tell the operating system what we want to happen. Okay, so that's that. So as an alternative, so we take FreeBSD, which is a Unix-based operating system. This guy does support multitasking. It also is a multi-user operating system. So we can imagine now, okay, we can have more than one program running at once, but we can also have more than one user running more than one program at once. Kind of on the other end of the spectrum, we're throwing all sorts of complexities in there now, right? Okay, so the shell executes a fork system call to create a process. So the shell is always running for an individual logged in user, and when the user types in, for instance, if I'm out here at the terminal, and I type in top like this, which is the name of a program that runs, when I press enter, it's going to fork the system call and make it and bring it to the foreground. So now the top program is running, and I can see all sorts of stuff that's running on my computer, and when I hit Q, it kills off that process. It didn't have to relaunch the shell. Shell was still there because that top program ran in its own thread of execution. Okay. Let's see. Yeah, here. The shell just waits for the process to terminate or continues with user commands. And we can kind of prove that if I tell, let's see, I think it's the and symbol. Yeah. So I just launched top there, and I ran it in the background. So top is running, and then I think I could do FG11488. Oh, it died. The guy doesn't know how to run in the background. Nice. But in any case, you can bring a running application to the foreground using the FG command. So kind of a good example would be, let's say we wrote a program with an infinite loop in it, like a Java program. I think we can probably mimic this. We have like a hello.java in here somewhere. Oh, I actually need to do. All right. We'll just do a while true. Int count is equal to 0. Print out count. Let's say count plus plus. Just to make sure this does what I expect it to do. Compile it. That's the end of the while. That's the end of that. What is it complaining about? Oh. That's what it's complaining about. I named it lowercase h, so I need to name that lowercase h. All right, so infinite loop, blah, blah, blah. So I'll go ahead and kill this. I'll try to kill this. All right, so now we'll run that exact same command, but in the background. Uh-oh. The virtual machine won't let me run it in the background? Oh, yes it will. I just need to give it the actual correct command. Oh, this is actually a good example for, this is a very good example for us. So even though this thing is running in the background, my Java program writes system.out.println writes the standard output, which is the console. So even though this program's running in the background technically, the Java virtual machine is making system write requests through the system call for the operating system, and it's still displaying on the screen I'm here. That program is running in the background. In fact, I might even be able to type stuff in here. I'm not getting enough CPU time in. It is running in the background, but the guy is constantly interrupting the CPU to do output. So this might actually be hard to kill. Did I get it? Did I nail it? Very interesting. So let's force quit that. Now, interestingly here, let's see if it indeed, let's just do a top. Is that program still running? It's not. Okay, so it killed off the program for me. So very interesting. So not the example I was trying to show, but still an interesting example. Okay, so in any case, back in the Unix days, programs would often exit with either an error code or a 0 if everything went fine. And that's evidenced if we see some old C programs. Let's see, do I have like a hello.c in here maybe? Yep. So here's an old C program, and notice that the main method here, in Java, main method is void. In C, the common main method returns an int, the error code. Did the program run to completion and work out okay? Or do I need to know that it errored out because of a IO error, or I wasn't able to retrieve the name of the file you entered wasn't a real file, that kind of stuff. Okay? This helps us in our programs when we are having one thing lead to another thing leading to another thing, knowing which of our applications died as part of that. Okay? All right. All right, so here's this idea of FreeBSD running multiple programs, and in our case, more complex, multiple users. We look at something called an interpreter. So something needs to sit in the middle, and really, what is that shell? Okay, so the shell has to go through some sort of program that's going to interpret what we're saying for the current user that's asking that program to launch, so they can keep track of who owns what and what should be displayed on whose screen and that kind of stuff. Also understand, well, here's an interesting question, I guess. In the early days of Unix, prior to the internet, even though Unix supported multiple users, how did more than one user use the computer at the same time? Was it one person on the chair, one each on each leg, and then Terminals. You learned about that in 150, right? Talked about it in 150 probably, this idea of these old terminals. So what did it look like before we had the internet? And Dr. Locklear actually still has a terminal system set up in the other room that, from a historical perspective, I guess is ridiculous. But but still interesting that they did exist. So the idea of a terminal is we basically had a monitor and a keyboard. This was prior to mice. And these guys were each physically connected through either a serial or a parallel port to that computer. So if you look at the terminal system we have set up in the other room here, there's a single serial box. Okay, serial box. Okay, that has a whole bunch of serial connections in it, and each one of those terminals would plug into it through a serial connection, and that would be its unique port. So it would interact with the Unix operating system that that serial box was connected to, where each user had its own little dummy, they're called dummy terminals, each little monitor and keyboard that allowed it to interact with the single operating system as one of potentially many users. So we did have an interesting thing from an operating system development perspective. There was this interesting threshold type thing where you had to decide how many users could potentially be using this operating system at once. In today's world, if you have a Unix operating system, and I mean you're supporting multiple users, how many users could how do users remote into a Unix operating system today? Do we still use dummy terminals? I mean, I guess the
It's
terminal simulator. So that's what this guy is, right? This is the terminal simulator. Okay, so it's running a shell, and I can through telnet remote into a machine and be using that machine. Okay? So how many users around the world could potentially do that at the same time? Very likely more than we can have physical connections in a building. So maybe we have 20 or 30 dummy terminals in a lab, and that's the number of dummy terminals we could have connected into one Unix machine back in the day, a long time ago. And your limitation is what? Based on the number of input ports on the serial box. So sometimes you'd have serial boxes connected to other serial boxes to stack the number of people you could have connected at once. All right, well now, today, we don't have that problem. So today, would it be unfathomable to have 1,000 users connected to a Unix operating system at the same time? Certainly could happen, right? 1,000, not a ridiculous number. Whereas back in the day, having 1,000 physical connections into a single terminal server was probably unlikely. I guess it's possible that it happened at some point, but I would actually doubt it did. That's a lot of individual users. Okay, so understand, if you're the developer or a group of developers who are making that old school Unix operating system, I mean, realistically, you're working with a different problem, right? The problem you're solving is, how do we give a reasonable end user experience for 12 people, 8 people, something like that, when each of those 8 people are each running their own single program. So even though I've shown here that, attempted to show, that Unix technically allows an individual user to run multiple programs in the background, that wasn't a real common thing. Okay, the way we used our operating systems back then was different than the way we use our operating systems today, where we're minimizing a zillion things and stuff like that. Back then, we were pretty much using one program at a time. Every now and then, you had somebody who was running some simulation software or something like that maybe would have 2 programs running at once. But generally speaking, 8 or 10 users means 8 or 10 programs that are running on the operating system. So you only had to make operating system level decisions as the person implementing the operating system, kind of like, what's the best way to manage the CPU? What's the best way to manage processes, to manage memory? You had to make those decisions based on your best guess on what would make those 8 or 10 people happy at once. Where today's world, we make different decisions, right? If we're making a multi-user operating system, these modern day Unix operating systems, 8 or 12 people, 8 or 10 people, we're going to go way above that, right? We're going to say maybe our average load of people might be 50 or 60 or 70. And really, when we think about the way our Unix operating systems are used today on a regular basis, I mean, most of us in here don't necessarily remote into a Unix operating system on a daily basis, right? How many of you in here have ever remoted into a Unix operating system and used it? My guess is very few, right? Okay. How many of you have ever used a Unix operating system remotely? Every one of you. Probably today. How did you use a remote Unix operating system today? Most of us have been on the internet at some point today. Pretty large percentage of the web servers on the internet are running on a Unix, some flavor of Unix-based operating system. So when you went to www.google.com, something like that, your machine made an individual request to Google, which spawned off a thread of execution within their web browser. So you kind of spawned off a program. So you ran a program on there, possibly temporarily, possibly for a long time, whatever it is. But you were part of the load on that machine. Does that make sense? So when you think about that, how many simultaneous users must Google's UNIX web server be able to handle? Rounding down, a whole lot, right? Okay, a lot of people at once, not 8 or 10. So our modern implementation, our modern design for these web server type approaches needs to take a lot more into consideration. It has to make very different decisions than they had to make 40 years ago. Make sense? All right. Okay, so, something else we want to kind of just compartmentalize as we're kind of thinking about things in terms of the data structures and stuff like that is the different types of programs that are running on a computer. So we have our user programs, and we're going to have our system programs. And system programs come in all sorts of different flavors. Some of them are really, really, really important. Some of them are kind of like, when you have some extra time on the CPU, do some work, but it's not real high priority stuff. So now we add a layer of complexity to that process scheduler, deciding which process gets the CPU next. Well, it's going to be a process that has a higher priority than the low priority ones. We're going to have two lines, right? One line of the dudes with lowest priority, they're only going to get some service if, there's just literally nothing else to do. And then we're going to have a line with higher priority. And then within that line, we're going to keep it sorted based on priority, right? So a priority queue is another data structure. Anybody know? I can't 100% guarantee I mentioned this in 300, but I typically do. Anybody know the data structure associated with a priority queue? It's called the heap data structure, HEAP. So we have a stack. Most operating systems have a stack to support recursion as well as a bunch of other things.
So heap does what?
Heap is a prioritized queue. So it's a line that when somebody gets into the line, they don't necessarily get into the back. They get to cut up to their priority.
So it's like several stacks within a queue?
It would actually likely have nothing to do with the stack. Just it's a line that is ordered based on your importance.
How do you determine importance of priority?
Let's keep it away from operating system level, just in real life. Whether you believe it or not, realistically speaking, if you're in line at McDonald's and the president walks in, chances are he's going to the front of the line. Secret Service guys, they're pulling pistols and stuff like that. But so using that as an example, so at some level, an agreement was made that that person has a higher priority in the McDonald's line than us peons, right? So when he got into the back of the line, he immediately was sorted towards the front. All right, so now it's a matter, so we take it back to the operating system level. How do we decide what programs have a higher priority than others? Well, realistically, from our perspective as users, we want the programs that we have said we want to launch to have the highest priority, right? We don't care about system call X, Y, and Z as long as our programs feel super, super fast. And as long as our operating system can maintain its stability and all that stuff. So we're relying on the operating system to make some of those extra decisions about, I kind of want Chrome to be the most important thing, but if something else needs to get in line in front of it sometimes to keep my computer from crashing, I'm okay with that. All right, so we're going to rely on that, but certainly we want our user programs to have a high priority, right? Certainly higher than the steerage that might be in line at McDonald's. So. Okay, but a heap, another one of those examples of a data structure that when you read about it in an operating systems book or something like that, did they not ever mention heap in chapter 1? No. It's usually one of those things that kind of gets thrown around like everybody knows what it means, and then you just assume it's really complicated. It's not. It means something very easy that just came up with. I don't know if heap is an intimidating data structure word, but you think of a linked list and you think, we tell you there's a data structure called a linked list, and we tell you there's a data structure called a heap, Probably we assume heap is more complex for whatever reason. I don't know. But that's all it is. It's a prioritized line. So in any case, there's going to be certain system level programs that belong to the operating system that are going to be important to the stability and the running of your operating system. And we want the operating system to have the decision-making process to decide which of those has the highest priority, which of those have lower priority, all that stuff. But at the end of the day, things that the operating system is going to do are going to go all the way across the gamut. We think about from a Java perspective. Java has something called automatic garbage collection. What's automatic garbage collection in the world of Java? Yeah, collecting unused memory. So, as our languages have evolved, we've looked at Java. We no longer have to request new memory and delete old memory. That's not our job. It's beneath us. Okay, so we have this garbage truck that's running around Java's fake memory, because Java is a virtual machine. So we have this garbage truck that's running around, and it sweeps up memory that's not currently being used. That is, memory that doesn't have any variables pointing at it. So a piece of memory whose pointer count is 0. Whenever we create a new variable that points at the same place, its pointer count goes up. 0, 1, 2, 3. As variables are deleted, goes down. Once it's 0, nothing points to it. We can't get to it. Might as well clean it up, right? That's what the automatic garbage collection does. Goes around, sweeps up the streets. Relatively low priority, right? We don't want our active program to be slowed down just to keep the Java streets clean, right? Clean them up when you get to it. If I'm running with a kilobyte of trash in memory that really needs to be cleaned up, not a big deal. Don't clean that up at the cost of Chrome running slower, something like that. Okay. Management. So this is just kind of giving us categories of what our different system programs are. They all shapes and sizes, let's say. Talked about that. We've kind of seen a picture of this layered approach where you have these different layers of your operating system, and each one kind of handles the interaction between the layers, deciding what we let through, what's allowed to be requested, that kind of stuff. The nice thing about this approach from a data structure perspective is we get to subdivide our operating system, let's say our kernel, into 2 or 3 layers. And each of those layers has a subset of tasks that it's responsible for. So you might say your operating system is really kind of 3 separate programs all running in terms of each other. And layer 1 communicates with layer 2, which communicates with layer 3, but layer 1 never talks directly to layer 3. Okay, so we can kind of organize the things that go into our operating system into these smaller pieces, and then expose those different chunks, the interfaces between them, I guess a little bit more targeted, in a more targeted manner. That doesn't sound as good as targetedly. So when we look at a traditional Unix system structure, again, thinking about the multi-user type world, as that makes things more complex. Instead of having the single user up top here, we have a collection of users. And each of those users is going to get their own shell with the same list of commands. They're going to have compilers and interpreters. They're going to have system libraries that are exposed to them. But this is duplicated over and over and over again for every single user. Okay. Then we're going to have this single layer, the system call interface to the kernel. So this is one layer that services all of these shells that are currently running on the operating system. Okay, so this guy is like the bouncer at the door. He handles what you're allowed to do with the operating system internals and what you're not. And see these layers here? So we have the bouncer, then we have the software level of our operating system. Then we have the internal bouncer. This guy he's in charge of the private room in the back. Okay, so this is the second bouncer that controls who's allowed to directly access the hardware. Okay, so that's kind of what I mean when we say an operating system is written in a layered approach. So bouncer for the software system calls, bouncer for the hardware physical calls. We can call them system calls. It doesn't really matter, but your hardware has circuits on it. And those circuits are little tiny programs that do something. So you're going to activate the read circuit that talks to the hard drive and pulls out a bit of information based on a read request, that kind of stuff. Okay. So that's just an example of what we just saw. Generally speaking today, if we were trying to decide what's the advantage of kind of a layered approach to writing operating systems, probably your end of the day single word answer is probably security, right? Realistically, it probably makes your code more modular, more bug free, or at least easier to manage, easier to update, that kind of stuff. But at the end of the day, it has to do with security. We have various checkpoints. You know, just like if you have a bar that has a bouncer that controls who's allowed to come inside and who's not. Okay, same thing's true here in our operating systems. Okay, so then we have this idea. This is kind of a, taking that layered approach one step further, the idea of a microkernel. So now we're going to take our operating system. I've mentioned up to this point that the kernel is the actual operating system, right? Well, now we're going to say the kernel is kind of the public face of the operating system. All right, it's the public face of the operating system. And then we have the microkernel, and these are the really important parts. Okay, so you have to go through a whole bunch of layers before you actually get to the microkernel. So a lot of that, if you look at this, this moves a whole bunch of what used to be considered part of the core operating system up, out into user space. Things that are like less precious, less important, need less security surrounding them. So maybe at the bar we don't hide everything behind the bouncer. Maybe only certain things are behind the bouncer, but maybe outside of the bar they have a place where you can sign up for a drawing or something like that. And maybe you don't have to pass the bouncer in order to sign up for the drawing. Okay, that kind of stuff, if it makes sense to you. All right, so that's the concept of the microkernel, is let's add one more layer and put all of our important stuff in one place. All right, we're at 8%, 10 minutes. Doing it. All right. Spent a lot of time programming this morning down in the cafeteria with some students. Let's see. That's why isn't Largen in this class? Or he's not in this class?
Yes.
Because he has the right kind of charger. You have the wrong kind of charger.
4.
5.
Oh, your computer, yeah.
Yeah. So
The old one.
you're useless to me is what I'm saying. He has the newer charger. He's less useless.
But he's useless right now.
Exactly.
So how can he be less useless if he's completely useless?
Well, that's completely useless. That's false hope. Okay. This isn't even hope. I'd rather have no hope than false hope. Because then you get your hopes up and then they're dashed. All right, so punchline of the microkernel, move as much crap into user space as we can, keeping only the really important crap inside the microkernel. Okay? Benefits. It's easier to extend a microkernel. So if you only have the core of your operating system at a very small level with only a relatively small number of ways of accessing it, small group of bouncers protecting it, to extend that kernel is much easier because now you can write a whole bunch of system level but kind of like user level applications that talk to the kernel in terms of those 4 or 5 bouncers. They all are interacting with the operating system through the same little communication channels. Okay, so easier to extend the kernel, easier to port the operating system to new architectures because now the actual operating system is that microkernel, so smaller program, less lines of code, easier to port. And then those user level applications they just need to be rewritten because they're all done in terms of the same set of requests. Okay, so easier to port is probably fair. More reliable, less chance of operating system crashing. If we say that 95% of all crashes occur, well, actually, you can say that 100% of all crashes are going to occur at the kernel level. They may not have started at the kernel level, but when it finally crashes, it is at the kernel level. The less stuff you have running in the kernel, the less places that things can break. Less moving parts, less things that can fail. And then the security is kind of obvious. Detriment performance overhead of user space to kernel space communication. So now you've moved a whole bunch of crap outside of the kernel, and now they're all vying for that kernel through the same couple of bouncers, 3 or 4 communication channels. So you've added another layer, and those communication channels, it's a resource now. The microkernel has become a system resource that now a large number of programs, system level and user level programs, are going to be interested in talking to, interacting with. So now we've added, a complexity for how do we manage that resource, which obviously anytime we're managing a resource, there's going to be performance consequences, right? All right. Mac OS X structure. So we see, I've mentioned this before. You will sleep soon unless plugged in. Ay, ay, ay. Yeah, that just dropped. The thing is, I don't want to. Let's just see this real quick. Well, let's just keep going. I don't want the recording to get damaged.
Want to use my charger?
I only have six sure.
Go.
Just watch as I plug it in, it's going to reset. Behind the back.
No?
False hope. The wrong kind. That's the old kind too. Yeah, is yours the new kind? Oh my god. All right, just go time. Just keep trucking. I do, but I'm not going to run all the way. We're fine. We only got 5 minutes left. When that drops to like 2%, we're bailing. Okay, so Mac OS X structure, we're seeing this is kind of a wrapper around Unix. So wrapper around BSD Unix. And underneath, we have this architecture, this mock architecture. So this would be a microkernel. Okay. Most modern operating systems use modules. Again, this is this idea of modular programming, creating functions that are different pieces talk through, that kind of stuff. Let's see. Solaris is another Unix operating system, so this gives us an example of its modular approach where, we have the microkernel in the middle, and then we have the stuff dealing with scheduling, the stuff dealing with device drivers, just compartmentalizing the different parts. So nothing, earth-shattering there. More recently, we talk about this idea of virtual machines, where that even creates another layer, right? So now we have everything running in software. So we have kind of an initial bouncer that acts. So we have a bouncer at the software level that talks to the next bouncer at the kernel level, well, at the user application level before it even starts talking to the operating system. So one more bouncer, one more layer of security, that type of stuff. So we're going to say virtual machines, more secure, do have a performance hit because we have one more layer we have to go through. And also we have an issue of what can they accomplish versus what can't they accomplish, because by having to go through one additional communication channel, we may have taken a couple of abilities off the table for them because they didn't have direct access to this. And we actually see an interesting thing, and we'll talk about it at some point, but Apple has a kind of an API they introduced a couple of years ago called Metal, M-E-T-A-L, Metal. And the idea of Metal is, sometimes your applications have parts of it that need to run really, really, really fast. And in order to do that, we need to give them direct access to the operating system. Well, because our modern operating system microkernel approach is all about layer after layer after layer after layer, what Metal does is a shortcut, like a toll road, if you will, that allows you to get right to the actual kernel. So we're going to get all the security, and then we're going to just bypass it. That's the approach of Metal for specific types of applications. So again, virtual machine stuff. And this is kind of going to be our homework assignment for Wednesday, is explore at least 2 different virtual machines, short little paper thing, nothing huge. But just looking at virtual machines, where they have worked and where they haven't worked. So I'm going to ask you to look at virtual machines from the perspective of, give me an example of a virtual machine that's been successful. Give me an example of a virtual machine that failed. Okay, where was it not the appropriate tool?
It's like, what's considered a failure?
Something that probably wasn't considered a success. You might find a good example might be the Solaris operating system tried to base itself on Java once upon a time, which had a bunch of virtual machine stuff, and that slowed the operating system way down. So stuff like that. So again, virtual machines, we have a couple different layers here. This para-virtualization stuff, it's kind of like, you know, how do we halvesy it? Where's a hybrid approach for virtualization type things? We're not going to get too much into virtual machines from this perspective, but how do you actually write a virtual machine where you have your host operating system, the operating system that your application that is a virtual computer, a computer written in software, runs on? Here's that Solaris 10 I was talking about. With it tried to run Java with a virtual side of things. Architecture, Java virtual machine. All right, so that's just system calls, not important. Bootstrap, not important. Okay, so that's that. I'll stop this before death happens. Homework assignment will be up here in about 5 minutes. Short paper, 2 to 3 pages, blah, blah, blah. All right, I'll see everybody on Wednesday.